Okay, good afternoon, everyone. My name is Andrei Faron. I'm a professor in applied physics. Welcome to the KNI seminar, distinguished seminar. Today the speaker is Professor Amir Safavi-Naeini from Stanford University. He's an assistant professor in the Department of Applied Physics. Amir is an undergraduate, has an undergraduate degree from University of Waterloo, and then he got his PhD from here at Caltech with Professor Oscar Painter in 2013. And then he joined Stanford as an assistant professor in 2014. And since then, he set up a very vibrant research group at Stanford, and he was awarded several prestigious fellowships like the Packard Fellowship, also the Terman Fellowship, and also the DARPA Young Investigator Award. He is doing a lot of very interesting work in the field of nanophotonics and quantum photonics, and today he will talk about his latest results on the quantum and classical optomechanical devices using lithium niobate. Please.
Thank you. Thanks for inviting me. It's nice to see so many familiar and unfamiliar faces. So today I'll be talking about two of the ongoing experiments in my group. One is on quantum acoustics, which is coupling these lithium niobate devices that are quite small compared to the size of a typical qubit, which I'll explain, and why we would want to do that. I'll try to motivate that a little bit. And also talk about some of the interesting photonic devices that we can implement on the same platform. These are the people who did the work. So this is my group back in July or June, I think. We have a very clever name, Laboratory of Integrated Nanoquantum Systems, which is LINX, and we make chip-scale quantum devices. So the work in our group is basically, very broadly, it falls into this Venn diagram where we try to control photonic excitations, phononic or mechanical excitations, and also microwave frequency circuits. And we make hybrid systems that fall on the boundary between these fields. So, for example, we have work on optomechanics. Where we're trying to do both classical and quantum modulation and transduction, and also work on beam steering. There's also, this relates to the work on quantum electro-optomechanics that I'll talk about. We also have an effort on photonics that I won't talk about today. This involves using thin-film lithium niobate optical structures. We're working with Marty Fayer's group and also Jelena Vučković's group in integrating highly interacting photonic circuits. And we also have some work just directly in circuit QED, which I also won't talk about today. Some of this is being done in conjunction with collaborators at SLAC, which is a DOE lab near Stanford. There we're trying to extend some of these microwave frequency systems up to millimeter wave frequency, so going to 100 and 300 gigahertz excitations. Okay, so here's some examples of things I won't talk about. This is work by Nathan Lee in my group. So Nathan implemented a chip, which is basically a very long resonator. And the different modes of this resonator can be coupled to each other through modulation. So there's a squid array at the end of this resonator that we can act as a time periodically modulated inductor, and we can basically couple these modes to each other and simulate a 1D lattice for photons. And we've been able to see things like Bloch oscillations. The y-axis here is time, so you start with the photon at the 0 lattice site, and it goes out and comes back, and we can see some oscillations here. So that's one thing. Another work which is related we were able to make a parametric oscillator. So this is basically it's a resonator with an inductor that's modulated at twice the resonance frequency. And the idea is that when you do that, you get an oscillator in sort of a classical system. So you start to oscillate, and those oscillations get clamped at some point due to things like loss. Here, the clamping is due to the strong nonlinearity of a junction array, and we were able to generate things that look a little bit like Schrodinger cat states in a system like this. Okay. So on to the things I actually want to talk about. So first I'll talk about our work on quantum acoustics with phononic crystals. So this is a graphic that was made by Wentao Jiang in my group. He's got an artistic bent. And the idea here was trying to spectroscopically observe the different energy levels corresponding to different numbers of phonons in a mechanical oscillator. And yeah, this work was really driven by Patricio Aranguez Arreola, who I think was going to PsyQuantum, and Alex Wolek in my group, and Mark, who was a postdoc who's now at IBM. So to motivate this, it's actually not so hard, thanks to the marketing department at Google. So people are trying to make these microwave quantum systems. It's hard because you have a lot of coherent circuits and you have to control all of them. So that means you have to have a lot of cables going into your fridge. And if you compare that to what you have inside your computer, laptop, or telephone, you have a chip that has billions of transistors, but only has 1,000 pins on the back. So you don't, at least for the classical technology, we don't need to control every single element. And so that's one aspect of these circuits. Another one is that microwave qubits are fairly big, especially these transmon qubits. They end up being hundreds of microns, and so if you want to have 100,000 physical qubits, you're talking about something like a 12-inch wafer, which is hard to do. And finally, we can't bring information out of the fridge, and so this has led to a lot of work from a variety of different groups and companies on trying to improve coherence time. So if you improve your coherence times, then you need fewer qubits to do something interesting. There's ideas on how to integrate the control down at the fridge, so that way you don't need to have a lot of cables going down. There's sort of hardware approaches to quantum error correction that are really interesting that people have been thinking about. One approach that I find really exciting is trying to make hardware efficient architecture. So control a larger Hilbert space using fewer control lines. And finally, finding ways of networking these systems is important, not just for quantum computing, but also if you want to use these quantum computers to do interesting sensing or networking applications. So if you look at a chip, this one is a chip from Google, so this is a few millimeters on each side. Google Santa Barbara, so this is something, so 5 years old now, 5 or 6 years old. This is something that processes microwave photons, and it's composed of a bunch of different types of elements, so these sort of linear elements. You can think of these as just cavities. These are for measuring, storing, filtering. There's weakly nonlinear elements. So this particular chip doesn't have any weakly nonlinear elements, but these are important for things like amplification or frequency conversion. And then there's strongly nonlinear elements, which are parts of these little crosses, which are the qubits. And the important thing is, so this is a transistor. If you're processing quantum information, you can't use transistors for your microwave frequency photons to generate interaction. And that's because the way transistors work, your electrons go from one side to another through a diffusion current. So that means they're bouncing around and generating a lot of sound, and they're telling the world, where they are and what direction they're going. So there's a lot of decoherence. These types of devices don't preserve coherence. So what people came up with were these Josephson junctions, and this is also involves tunneling, but now you're talking about tunneling of Cooper pairs that's mediated essentially by virtual phonon. So it's not, the tunneling doesn't involve leaking any information out to the environment. So these structures don't generate entanglement with the environment. They don't generate any decoherence. And so we can make these. So this is a picture of the our evaporator in the lab. We evaporate two lines of lithium niobate, aluminum, overlap them, and where they overlap, we've grown an oxide. So that's a junction basically. And this junction goes here. So if you look at this, 100 nanometers, so it's blown up by 1,000 times. This little junction goes there, and this is basically also aluminum. This is one plate of a capacitor, and there's a capacitance to ground. So the ground plane is what's surrounding it, and so now you have a capacitance, and your junction here acts essentially as an inductor. So you have an LC circuit, and an LC circuit, you can think of it as a harmonic oscillator. So there's a degree of freedom, which is the phase, and there's another degree of freedom, which is the charge, and they're complementary the same way position and momentum are complementary. So that charge degree of freedom, basically through the energy of a capacitor, it's Q squared over C, so that's quadratic. The phase degree of freedom, to figure out how what that looks like, what the energy of the phase looks like, you have to learn a little bit about learn a little bit about the physics of Josephson junctions. Basically, it turns out that the energy of a Josephson junction goes as the cosine of the phase across it. And I mean, you can think of this in many different ways. So this phase is a number that completely defines the state of all the electrons in the superconductor, or all the Cooper pairs in the superconductor. And you can, these phases are normally constant across your superconductor, but now that you have an insulator, they can be different, but they want to be close to each other. So this cosine is what kind of forces them to be close to each other. Okay, and then we can basically take this circuit, we can look at its Hamiltonian. There's that charging energy, Q squared over C. There's this Josephson energy, and we can expand this Josephson energy to some low order, so we can take it up to second order, and this is effectively acts like a harmonic oscillator. And you can do that as long as your ground state wave function is highly localized in phi, so it kind of dies out, and so it only samples the a very small part of the this phase. So and to get that, you have to make the capacitance very large, and that's how transmon devices work. So that gives you your two-level system, and then you need to control it. So there's a few ways of controlling these circuits. You can change the Josephson energy by basically splitting a junction into two junctions and making a squid. So a current would then change the energy. So effectively, you're controlling sigma z. And you can drive X and Y by sending a voltage in. And now, so this gives you full control of the qubit. You want to do readout. The way to do that is to use a readout resonator. So if you have a resonator that's coupled dispersively to the qubit, dispersively meaning that the resonator frequency is very different than the qubit transition frequency, then the frequency of this resonator ends up being a function of the state of the qubit. So if the state is ground or excited, you get a phase shift. And so by just reading out the resonance frequency or phase shift of a coherent tone that's propagating through this waveguide, we can do a readout of the qubit. Okay, so then you can extend this further and further to do 2 qubit gates, etc. I won't go through all that, but I'll just say that this is what people are thinking about. I think I stole this from some Google document. I don't even remember anymore. I should probably cite it. This is being recorded, right? Yeah. So And the approach is, you have a lot of qubits. Each of these qubits encodes, you use a sort of 0-1 state of these qubits, and then you create a lattice of these. And then here, what they're proposing to do is bring the readout, the readout layer is kind of brought in through another chip. And that's the readout and the control. Okay, so an alternate approach are these hardware-efficient architectures, and an example of that is the really beautiful work coming from Yale, from Rob Shulkoff and Michel Devoret, Steve Gervin's groups, where you use the qubit essentially to process the state of a harmonic oscillator. And then you have a larger degree of freedom, a larger space to deal with. And instead of doing your error correction by having many qubits and that behave as one qubit, you can do your error correction on this state of this bosonic degree of freedom. And these are examples of sort of logical qubits. These are actually not logical qubits, but sort of these are examples of states of these oscillators that have been generated. And a complementary approach is to have one qubit. So this is a qubit from Dave Schuster's group at University of Chicago that controls the state of many harmonic oscillators. So each of these is a microwave resonator. So there's something like 10 microwave resonators here. And this one qubit with a single drive line or maybe two control lines is used to control the state of in the 0-1 photon state of these resonators. So again, it's the same idea. You use the nonlinear element as a controller. And what we want to do follows sort of trivially from this approach. We're basically hoping to replace all of those microwave resonators with mechanical resonators. Okay, so how do you compare this standard approach to this random access approach? So in the standard approach, you have n qubits and there's gates, and you can do these gates simultaneously. These are 2 qubit gates between your qubits, and let's even forget that there's any geometric limitation on the range of the interactions. So let's say we can do any 2 qubits, and they can all be done simultaneously. In the random access approach, we have this processing qubit, we have these mechanical storage qubits. And now, it's sort of a naive way of doing things is to, if I want to do a gate between 2 mechanical resonators, I can do a swap to a qubit, I can do a qubit mechanical gate, and then I can swap back. And so now effectively I've done a gate between these 2 qubits, or these 2 mechanical resonators. And so this way I can sort of mimic this serially. So instead of doing everything in parallel, you do it serially. So the nice thing is that this is programmable and it's hardware efficient. It's hardware efficient in the sense that I really only need to, there's only one control line. It's just the control line to this qubit. And so for this is, following the Dave Schuster's work, that we proposed this, and the people at Yale have also thought about how this can be done actually with everything in parallel by using virtual transitions. Okay. So to estimate the error, we have to take into account that these gates are being done serially, and we'll go through the details. But this is the result for the 2 qubit the sort of gate error that you would expect here, and it's pretty easy to understand. So you have one term that goes as 1 over g, where g is the interaction rate. And it goes as the 1 over g because the faster you do the gates, the lower the error will be. And then the qubit error and the resonator error rates come in, are basically divided by g. And the reason there's an n in front of the resonator is because your n resonators have to wait while these gates are being done. And so here we have n resonators, and they're spread out in frequency. But if we just keep adding more and more resonators, or if we increase that coupling, you're going to end up having interactions between these resonators that are at different frequencies, because it's all happening through the same physical system. So there's crosstalk. The only reason there's no crosstalk is because they're at different frequencies. So if the interactions end up being very fast, you end up having crosstalk. And so you get a crosstalk term that scales as it scales as g squared and n squared. And so what's interesting about this formula is that this error per gate is minimized for some g. So if you give me an n and I know these, I can tell you what the g I should aim for in my hardware is. Okay, so, oops. Yeah, so so basically this is the kind of optimal coupling for a number of resonators. And now that we have that, we have to ask another question, which is, what kind of gives you the most quantum capability? And because I really don't know what the right answer to this is, this paper has a metric called the quantum volume, which seems okay, so we'll use that. I don't really know what that means, so that's the caveat. But the way it's calculated is, your circuit has a width and it has a depth. And the depth we call the number of operations you do before you have a single error. So that scales as 1 over n times this error. And the volume is basically the sort of maximum square that you can fit in this. So this makes it unattractive to have a single qubit that I can do a lot of operations on, because that's not very exciting. And also if you have a lot of qubits, but you can only do one operation, that's also not very exciting. So it sort of tries to strike a balance between these two. And just for context, this recent Google result, the quantum volume is around 1,000. Okay, so now that we have this optimal coupling, we get an effective error per gate, and that's going up as the number of resonators goes up. And if we multiply these by each other, you end up with a curve. And the maximum quantum volume is basically the biggest square that I can fit in here. And that ends up being around 200 for numbers that at the time we thought were realistic. And now if we go back, that gives us the number of resonators we want and the g that we want. So the optimal parameters would be a g of between 1 and 10 megahertz, a mechanical Q of around 10 to the 8, and something like 15 resonators. Okay, so this is what we're trying to go for. So so what are the actual hardware challenges in trying to implement this? I mean, one is, how do you make ultra-coherent gigahertz mechanical oscillators? The other one is, how do we couple these mechanical oscillators to qubits? How do we couple them well so we get fast operation? So how do we increase G? And we also need to really reduce the number of spurious modes, because the problem with using mechanical waves is that mechanical wavelengths are short. So if I have any volume, it's going to have a lot of different mechanical modes, and you don't want to couple to them. And you have to do all of this while your processing qubit has large coherence. Yeah.
Are you referring to T1 as coherence? Are you assuming no pure dephasing?
Yeah, I mean, we can call it lifetime. I mean, you want both to be large. Yeah, I'm not distinguishing between them. So it's T1 and T2. Have to be good. Yeah. Yeah. So, and the sort of one figure of merit that might be interesting is this G multiplied by the minimum of the T1 times. And I'm assuming your T2s are T1 limited. So in the microwave hardware, pure microwave hardware, this number is around 10 to the 4. And in practice, they get something like 10 to the 3. Okay, so for coherence, at least this is work from Oscar Painter's group. They've been able to show T1s of around 1 second. So the T2s aren't quite as good, I understand, but the T1s are very good. And the T2s are still better than the best on-chip microwave resonators. So these are all mechanical resonators of the same frequency. It's a very small mechanical resonator. And the key thing that makes this work are these phononic crystals. The idea is you have a periodic lattice. So if you have a periodic lattice of atoms, you get these bands for electrons. If you have a periodic lattice in a dielectric, through Maxwell's equations, you end up with photonic bands, and through the equations of elasticity, you end up with phononic band structures. And this also means that you can now generate phononic band gaps. So you can have regions in frequency where there's no mechanical excitation of any polarization allowed. And this is important for a couple of reasons. So having a gap that's large makes these structures robust to fabrication. And things like isotopic imperfections, because if you have, like, let's say you make a defect in a crystal like this, that means you have something at a frequency that's within this gap. Now if I perturb this structure, it'll cause these edges to move around, it'll cause the edges to smear, but the amount of disorder you'll get is just from, as long as it's smaller than the gap, which is enormous here, it's something like 20%, as long as your disorder is less than 20%, this mode stays high Q. So that's very different than what we have in photonic structures, where disorder causes loss because it causes coupling to radiation. Here, phonons can't radiate, so disorder actually, making a good phononic band gap actually makes you robust to disorder, at least to linear scattering. And this means that the primary loss mechanism ends up being things like two-level systems, as long as you work in a good material. Okay, the next thing is, how do you couple mechanical resonators to qubits? And there's a long tradition in doing this. So this is from about 10 years ago now, from Andrew Cleland's group, coupling an F-bar resonator. There's work from Yale coupling these sort of bulk acoustic wave systems. So these curves are these sort of strong coupling curves. So they show the resonator mode crossing the qubit mode, or the qubit mode crossing the resonator mode, depending on whose work you're looking at. It's always the qubit mode crossing the mechanical mode. And so our approach is basically these 1D phononic crystals, and that's what I'll talk about. Okay, so there's also another key difference between the optomechanical approach, where these results were measured. So here, your Hamiltonian is this nonlinear Hamiltonian. So you couple your photons to your phonons through optical driving. And this works with any material with good properties. On the other hand, for the piezoelectric coupling, where you're directly coupling to a qubit, you're looking for this sort of XX or beam splitter type coupling. And this needs a piezoelectric material where your strain generates a polarization. So for our work, we use lithium niobate. It's crystalline. It has a very large piezoelectric coefficient, one of the largest, and it also, we've figured out how to make structures out of it. Okay, and then finally, you have to do all this while maintaining good coherence times for the qubits. And the challenge here is basically these kind of spurious phonon couplings cause qubit decoherence. Basically, if you have many phonon modes here, you're coupling to a large bath with many degrees of freedom, and it's unlikely that you'll get your excitation back. What we have is a qubit coupled to mechanics, but we actually have this mechanics coupled to many different modes. In this demonstration by Andrew Cleland group a few years ago. And then the qubit itself is also coupled to a bunch of spurious modes. So what we want is basically no coupling between the mechanics or the qubit and these spurious modes. And that's, you can do this in a phononic crystal, because now if your qubit frequency is also in this band gap, there's no modes to couple to. So you eliminate also that channel of decoherence. So here's an example. This is a simulation of a type of resonator that's commonly used in the MEMS community. They have fairly good Qs. It's basically an interdigitated transducer on a thin film of lithium niobate, or it can be any material that's piezoelectric. And if you look at if you couple a qubit to this capacitor and you look at the T1 of the qubit, it will be terrible. It'll be something like 10 to the minus 9. And that's because there's a lot of modes within this device that you're coupling to that lead to essentially a resistive bath, anomic bath. If you go to these phononic crystals, you get something like 10 to the 5 increase in the coherence time. So that's how we. So the phononic crystal both makes the mechanical lifetime longer, and it makes the qubit lifetime longer, and that's why we're using it. Okay, so this is our first device. It's a qubit. These are control lines that I talked about. This is a readout resonator, and it's coupled to a bunch of mechanical resonators. So under an SCM, it looks like this. So we have a thin film of lithium niobate with multiple resonators. And our qubit is coupled to these 5 mechanical modes, one mode inside each of these defect sites. Under an SCM, this is what it looks like. It's actually, this structure was a little bit dirty, so you can see some polymer on the sidewalls, and that's one of the reasons our quality factors were limited, and we're working on that. This is a simulation of what the mechanical mode should look like. So it's a sort of a shear wave, in-plane shear wave that's confined just to this little box. And then we wire bond the chip, we put it inside the fridge, and we cool it down. So this is right before we put the shielding on. Okay, so one of the things we do is we sweep the qubit frequency, and as you sweep it, you see a series of anti-crossings, and these correspond to the different mechanical modes in the structure. There's also some anti-crossings that we understand a little bit better now. This is basically our band gap had actually already ended a little further up. So these are probably standing waves or waves inside the shielding structure. These are the numbers. So we get Gs of around 15 megahertz. Our line widths are at around half a megahertz for both the qubit and the mechanics. And so even though we're quite a ways away from state of art, we're still in the strong coupling regime. And in fact, it's better than strong coupling because the coupling is strong enough that we can actually detune the qubit from the mechanical resonator and still have to second order an appreciable coupling rate. So we end up with a term in our Hamiltonian when the qubit is detuned that looks like A dagger A multiplied by the qubit energy, and the coefficient in front of this is something like 3 megahertz, which is still larger than our decoherence rates. Okay, so for our experiment, we do this thing where we put the qubit at a lower frequency, we excite the mechanics using a coherent drive, and then we read out the state of the qubit. And we see that basically when there's multiple phonon excitations in the mechanical resonator, the qubit line splits, and this agrees. The light blue curve, or the light blue area, and the black curve is theory, and there's just one fit parameter here for the drive. Okay, so this allows us to see this phonon number splitting effect, and this is sort of the first step to trying to do more complicated dynamics with phonons. So if we want to do generating things like cat states with the phonons, we have to be deep into this regime to be able to do these sorts of things, and that's what we're working towards. Okay, so just taking a step back, I was trying to look at a little bit of the literature on quantum mechanics, and there's this paper by Einstein in 1907, which is on basically the theory of black bodies. And in this paper, he says that for Planck's theory to be correct, you have to quantize motion of all ions and all mechanical systems inside your bath. And what's interesting is he actually in the in a footnote, he says, it is obvious that this assumption also, and so the levels will be 0, h bar omega, 2 h bar omega, etc. And then he says, it is obvious that this assumption also has to be extended to bodies of capable oscillation that consist of any number of elementary structures. I thought that was surprising that Einstein had thought about this, 10 years before Bohr's atom, which quantized the orbits of electrons. Okay, so, but there is something that Einstein wouldn't have known at the time, which is actually trying to detect this quantization is non-trivial, and I mean, imagine you're trying to see the quantization of your different phonon levels by measuring the position. So if you do that, you get a signal which is position, and there's some noise, and well, energy goes as that signal squared, so you want to square the signal, and then you want to average it over many cycles to get an estimate of your energy. And if you do that, you're also squaring your noise, and I'm going to assume that my noise and my position are uncorrelated, which opens a whole bag of worms, or can of worms. Why would you have a bag of worms? But this leads to an uncertainty in the energy, or imprecision in the energy. And if you want to have small back action, so you want to disturb the energy of the system by less than h bar omega to be able to distinguish the different energy levels from each other, that automatically implies that this delta x squared has to be larger than h bar over 2 omega. So this means that your imprecision in the energy ends up being larger than h bar omega. And I mean, we can even say something stronger about trying to measure quantization using linear detectors. But I first learned about this paper from Haixing Miao and Yanbai Chen, which is like one of the most underappreciated papers in the field. People should really read this. But basically the solution is that you have to be really careful not to measure position if you're trying to measure quantization. And so one way of understanding quantization of the phonon levels, and so one way of understanding how the qubit detector works is that the detector itself is sufficiently nonlinear that it does that first step of squaring the signal without telling you anything about the position itself. So it gives you directly the square of the signal. So you're never learning what the signal is, you're just learning what its square is. And then this argument about the back action doesn't hold. I thought that was interesting. Okay, so yeah, just as a retrospective, this is the sort of state of the art in quantum acoustics, and this is this number of operations metric that I talked about. So 10 years ago, we were at around 2, and now we're at around 26. So this might not look like a lot of advance over 10 years, but actually, I think that these new approaches from our group and from several of the other groups are very different than the initial approach, and they have a lot of room for improvement. So I'm quite optimistic that we'll be able to get to these 10 to the 4, 10 to the 5 numbers in the next few years, and that could give us an order of magnitude increase in the quantum volume of these microwave systems. And after all, you just need a few orders of magnitude, right, to go from yeah. Okay, so here's another beautiful artwork by Wen Tao, and I want to talk a little bit about same type of structures, except for we're using them for something else, for transduction of microwave photons to optical photons. And so this is a photonic crystal made, it's a representation of a photonic crystal made out of lithium niobate, and he's showing that, microwaves come in, optics comes in, and optics goes out. So before, I want to really distinguish between two different things. So a modulator, an optical modulator, is something that the internet runs on these. Basically, it's a device where you send in a microwave signal, and it imparts that information onto your optical signal. So in a way, you're using low intensity light to make a measurement of a microwave signal. That's what a modulator is. And state converter, the structures look very similar, but they're used in a different way. So in a state converter, you send in a microwave photon and out comes an optical photon. So you're not making a measurement because you're sort of destroying the signal that's coming in perfectly and it's being converted. And it also just practically, there's different figures of merit that matter for these two different things. So on the classical side, these modulators, what you really care about is sending in as little microwave signal as possible to modulate your light field. And on the quantum converter side, what matters is you're trying to not heat up your fridge. So you want to dump a low optical power into your fridge for every qubit that you're converting. Okay, so talking about modulation, there's some debate as to whether piezo-optomechanical or electro-optic coupling, which one is better. And if you just look at the sort of the physics of the problem, you have a voltage drops across a medium over a certain width, generates an electric field. The electric field through some material parameter generates a change in the index. So this is this parameter, material parameter, is something like 30 picometers per volt. So that gives you how much index change you expect. And if you make a piezo-optomechanical system, you have a block of material and it's got a certain width, and now I put a voltage across it. This generates an electric field. Electric field through the piezoelectric tensor generates strain. And then strain generates either displacement or through the photoelastic tensor generates a change in the index. And now I can multiply these two parameters by each other and I get something like 15 picometers per volt. So at least naively, it seems like you might as well just use the electro-optic effect. The piezo and photoelastic tensor together, they don't seem to give you something that's significantly better. But this actually isn't true. And we've been able to get these piezo-optical mechanical modulation that effectively gives you something that's 100 times larger than this. And that's what I'll talk about. But going back to state conversion, which is again a very related problem. So the way, just a quick review of how these quantum state converters work, you have an optical system, a mechanical system, or a microwave system, and you have the optomechanical interaction. You drive a laser, which linearizes this interaction. It turns it into that. And then the cavity drops out a few of these terms, and now you're left with a beam splitter interaction. And then what you do is you adiabatically eliminate the optical cavity. So you say that the optical cavity is very fast, kappa is large. That means it follows the mechanical amplitude. And now I can substitute A back into this equation, and I end up with an equation just for my mechanical system or microwave system, where I have an extra damping term. In this damping term, you can call it the measurement rate, the cooling rate, laser cooling rate. Either way, it's another damping channel that's opened up to the microwave system. So the way that you efficiently convert an incoming microwave photon into an optical photon is by essentially matching these two loss channels. So your microwaves or mechanical systems, these two loss channels, one into the light field, one into the motional degree of freedom. And if you match these two, this is your condition, then an excitation coming in just tunnels through. Okay, so to answer this question about the figure of merit for the converter, the important thing is how much pump power are you dissipating for every qubit that you're converting. And so this matching condition from the previous page, it implies a certain amount of power because this G scales as the number of pump photons. And it also implies a bandwidth. And whenever you have a power and a bandwidth, you can divide them to get energy per bit. So the energy per bit here ends up being kappa over G naught squared. where G naught is your sort of single photon coupling rate and kappa is your loss rate. And so in optomechanics, this is about 1 megahertz in the sort of silicon optomechanical systems. In the best electro-optic systems, the ones that have been highly optimized, this is on the order of 1 kilohertz. And the kappas are maybe a little bit better in the electro-optic system. So, so at least this seems to point to optomechanics being a viable way of doing state conversion. If what you care about is just rates, doing conversion at a high rate. And the approach, I mean, the important thing is you really want to improve this G naught. You want to improve this optomechanical coupling. This G naught squared scales as 1 over V. So the idea is you localize your mechanics and your optics into a small mode volume to maximize this. And we've been able to make these photonic crystals on lithium niobate, where we get high Q and we get G naughts on the order of about 100 kilohertz. Okay, so at least the G naught problem is solved. The G naught is now improved over. But now the problem is, how do I actually connect this to a microwave line? Because you want to have a converter that has a microwave input and optical input. And this is very difficult to couple to because it's very small. So when something is small, you need to have large forces to drive its motion. So for anything, you need to have large forces. And so if you have big capacitors, you can generate a large amount of force. But if you have small capacitors, you have to sort of increase the field per photon that drops across that small capacitor. And that's the same as increasing the impedance. So that's one way of coupling to these very small mechanical modes using high impedance circuits. Or two, you can use a large capacitor and then you can focus those sound waves down to a small volume. Okay, and I'm slowly running out of time, so I'll speed up a little bit. But this is the first approach, the sort of high impedance approach. So this is a circuit. This is an LC circuit. It kind of looks like an L and a C. This is how we couple linearly to the circuit. So how we excite it. That's the blue line, and the red line is how we tune. So this is a tunable LC circuit because these are all little squids. So we can change the magnetic field going through them, and you can move that around. Okay, and I really like these pictures because they give you a sense of scale. So this is what it looks like, and if I zoom in, this little thing here is the mechanical oscillator. So this is a 6 gigahertz mechanical oscillator made out of lithium niobate. This is an aluminum electrode that comes up to it but doesn't touch it, and it drops its electric field across the lithium niobate. And on the other side, we have this array of squids, and each of these are 2 junctions, and this is where the magnetic field goes to change the frequency. Okay, and the mechanical modes we're looking at are something like this. So this is, again, a phononic crystal. There's a localized mechanical mode that generates a potential that looks like that. And here, this thing oscillates according to simulations at 6.4 gigahertz. In the real world, it oscillates at around 6 gigahertz. We can tune that LC resonator's frequency over a very large range, from around 8 gigahertz down to below 6 gigahertz, and we observe an anti-crossing with our mechanical mode, which tells us that we have a cooperativity of 4, which means that when they're resonant, an excitation in that mechanical resonator is more likely to leak out is much more likely to leak out as a microwave photon than any other channel. Okay, so that's the first approach, using high impedance circuits. The second approach is a sort of acoustic impedance matching. So instead of increasing your impedance by using a junction array or a very large inductor, what you can do is use big capacitors that generate force over a large area, so they generate a lot of force, and then convert that into focus that energy down to a small place. And so this is really a type of lever. Piezoelectricity generates large forces, and what a lever does is it converts a large force, small displacement into a small force, large displacement. So that's what the structure does. So it's just a sort of a dynamic lever. And so what we were doing is trying to design these. And one of the things we discovered was that it's actually not totally trivial to design these types of structures. And basically, what you're trying to do is match the mode structure on one side, where you have the transducer, to the mode structure on the other side, where you just have a waveguide. So this is a transducer with electrodes on it, and this is the waveguide we're trying to excite. And if you just do things adiabatically, it won't work, because basically, unlike electromagnetics, where I can take a waveguide and make it larger and larger, and the fundamental mode essentially stays the same, it just gets bigger and bigger. Here, when you go from a narrow waveguide to a large waveguide, the modes end up getting localized at the edges. So in mechanics, the edges are always the slowest waves, and so the fundamental modes of a waveguide are always at the edges. There are always these edge modes. And edge modes don't couple well to electrodes, which are in the middle. So basically our solution was the laziest solution, which is, don't go to a very wide transducer, go to a narrow transducer, but just make it long. And these are room temperature measurements showing that we can get something like 10% of the energy into these types of waveguides. So finally, I just want to say that we have combined these types of transducer structures with our optomechanical system. It starts to look a little bit like a Rube Goldberg machine. So you have microwaves coming in. They excite in this long transducer. They excite propagating acoustic waves that are then focused down into a waveguide. And this waveguide goes in and excites the localized mechanical mode. So this is a simulation of how we're exciting this mechanical mode. This is our optical mode. And in these types of modulators, we've been able to see V-pi's of around 0.02 volts. So the kind of commercial lithium niobate modulators are something like 100 times larger V-pi. So that's the voltage you need to generate a phase shift. They are resonant, so that you have to be resonant for this to work. Resonant with the mechanical mode. And just going back to this slide, I mean, essentially what we've done here is, so we have a voltage generating electric field generates strain, and then this focusing effectively focuses that strain into a small mode volume, and so we end up getting a much larger effective electro-optic coefficient. Okay, so with that, I want to thank the funding agencies, and here's some references for the works that I talked about today. Thanks.
Some questions, and I'll ask you that you use the microphone for questions. So for the last devices that you saw, you did testing only at room temperature?
These were just room temperature.
Okay.
Yeah.
And when you cool them down, like what are the prospects of your transaction efficiency?
We have not cooled them down. If we cool them down, so this is the efficiency per photon, so it's 10 to the minus 8. And I think we can get to 10 to the minus 5 or 10 to the minus 4 efficiency in these systems. Yep.
Very nice talk. So for the qubit, you emphasize that you want your qubit to interact with one mode only and not with the spurious modes.
Yeah.
So it seems like there might be a similar situation here with the optomechanical crystals and the continuum of modes that are propagating in the waveguide. Is that a concern, or?
Yeah, that's a great question. So the so basically what that, I think what you're asking is actually you could be asking one of two things. So one is, what about higher order modes of this waveguide? And then the other thing is, what about standing waves within this waveguide? Okay, so you're talking about standing waves. Right, so if this electrode transducer, if this is actually matching to 50 ohms, then that shouldn't be a problem. There shouldn't be any standing waves. Right. Yeah, so I think right now this structure is not matched to 50 ohms. So there probably are some standing waves. And I think we have some, I don't have those plots here, but if you look at the structure of this structure, it's got a few peaks, and those are probably standing waves.
Any other questions? Okay, Michael, wait. No, because it's recorded, so I think it's.
Admixture of X.
Sorry, what?
So you talked about X squared,
Mm-hmm.
the need for X squared measurements.
Yeah, yeah.
This is something that I wondered about. Presumably, if there's a little bit of admixture of X,
Mm-hmm.
in your X squared
Yeah.
transduction, that will foreshorten the life of those quantum states.
Yes.
But
Yeah.
has anybody calculated that, or do you know anything about it?
Yeah, I mean, so that is a source of decoherence. In its so there's schemes for, so when you have a resonator which is used for readout, and it's being used to read out a qubit, and they're off resonant, you're hoping to only have the dispersive interaction, but you still have some leakage through the sort of tails of that Laurentian. So there's a few approaches to that. One is, so here we have sort of a converse case. So we have, the qubit is, the tails of the qubit can, the phonons can leak out through the qubit. So there's one approach, is it's called Purcell filters. So I don't know if you've heard of these things, but they're basically a filter that has multiple poles. So the tails of that Laurentian drop off faster than delta squared, and you can set up a situation where you might have a pole in the transmission through some sort of coherent interference, and then you put your qubit there, and that can also reduce that. Does that answer?
Other questions?
I think exactly in this context, I don't think so, but I think it's a similar problem to that. Yep.
Okay, well, if there are no more questions, let's thank the speaker one more time.
Okay, thanks.